Because when you send the abstract, it's so early before the conference that things have changed since then. And I've done experiments with proton conductors after that, and I think I would like to talk to you about the proton conductors, which are extremely important. So first I will talk about the ICARUS 9 experiment. In 1996, 20 years ago, Stan Pons gave a talk at the conference here in Japan, Kaido conference, and he showed this ICARUS 9 cell, which is a double-stage cell. The bottom of the cell is for, let me see if I'm correct now. Yeah. At the bottom of the cell is the electrolytic part, and the top is it's the cooling system, so that the water vapor will condensate and come back, so that you can run it at boiling temperature for a long period of time without having to add any water. So there are three levels of temperature measurements, inside and outside of the casing, which is aluminum. The outside, the whole thing is a constant temperature band. So the outside temperature is constant, but the inside temperature varies. So this is the bottom is the hotter place. This is a little cooler and a little cooler there. There's a viewport so you can check the level of water in the cell. So here's my system. It's a water tank and constant temperature bath and the this is a view of the bottom of the cell. It's in a Pyrex tube with the electrode. I can run two different types of electrodes. I run the 12 millimeter and 100 millimeter for the cathode. I used palladium silver, 60% palladium, 40% silver from Johnson Matthey. And here we have 4 graphs showing temperatures. There's a thermistor inside the cell to measure its temperature. So you can see that depending on the power input, you have this part is sensitive, and then this other part is sensitive, and this other part is sensitive. So depending on the power input, you have different sensitivities. The maximum with this design is 65 watts. Above that, the boiling is too strong, and the water vapor will go out. This calorimeter needs calibration with the platinum cathode, same dimension as the palladium cathode. The maximum power is 65 watts. I remind you that ICARUS 2 had only 10 watts maximum power you could put in. You can use different regimes according to the temperature. To the power, sorry. First experiment I've done with a 12 millimeter cathode for 60 days of loading at 200 milliamps. And then I increased the power to 500 milliamps, but I didn't see any excessive. But this is exactly similar to what was happened in 1996. There was no excessive. So at the present I'm running a 100 millimeter cathode, and we are already waiting 30 days. So it's working by itself at home now. Now let's go to the solid-state electrolytes, which are proton conductors. You might know that most of the metals conduct electricity with electrons, obviously, but in some materials, electricity can be carried away by protons if you have hydrogen in the sample. This idea came from Francis Forat, patented the design in 1989. So he has patents, French patents. Now it's over. Conduction is by protons or deuteriums. You're using a crystal called lanthanum aluminum oxide. And when it's stoichiometric, it's white, the insulator. But if you have lanthanum vacancies in it, 1 minus X, then the vacancy makes it color centers, and it becomes an insulator, but it is red. I will show you. When you put deuterium in it or hydrogen, the lanthanum is having a valence of 3, is replaced by 3 deuterium. Let me show you what it looks like. Here is the lanthanum aluminum oxide heated in air, or as we see it, it is red. When you heat it in hydrogen and deuterium, it will become white. If you heat it in air again, it comes back there. It's a reversible process. I've designed a heat flow calorimeter adapted to this experiment. So it's a 35 millimeter tube, stainless steel tube, in which I put the sample. And there are 17 thermometers inside here, an insulating material here, and 17 thermocouples outside. And the whole thing is in a water bath at constant temperature. So, because it's like a CMEC calorimeter but simplified, because of the symmetry of the system, you don't need to put that many thermometers, the thermistors. Actually, I'm using K-type. Okay, here is the design of the top of the cell where the experiment is happening. Let me show you that. I have two plates, two stainless steel plates that squeeze the system. This is a heater. It's a macro with holes where I put a Cantal wire as a heater. There is the crystal is here, and there is a cathode, anode, two plates, and I can pass the current between those two plates. So first I have to heat up the sample at a pretty high temperature so that conductivity happens, and then I can put a current through the two plates, and the proton conductor will be active. I put a thermocouple here in between the cathode and the heater, so that to measure temperature also. Oh, it's here, I'm sorry. I made a mistake. It's on the other side. Well, anyway, I'm sorry. This should be here. Let me show you a view of that. Here's a view of the system. This is the design. Okay, this is the cell itself. This is the outer cell and mounted system. So I have to calibrate the system first. When I put the heater alone, I have the voltage, millivolts, versus the power input, and it's pretty much a smooth curve. It's not linear because there are losses in my design, but it's calibration. Now, when as soon as I add a voltage, this is the temperature, I'm sorry, I've calibrated both the voltage and also the thermocouple that's inside. So I can use the two indications. I realize that to make sure you don't make any mistakes, you need at least two informations, you know. It's not because you find a Roman coin in the floor that the Romans came here. Maybe someone dropped it. So you need two indications at minimum to make sure you're correct. So now I apply a voltage through the proton conductor. And I go from this point to that point. The power input is this distance. And the temperature goes up here. So it's above the calibration curve. That means there is excess heat. So to find out the excess heat, I have to just go to the calibration curve. And this is the distance that shows the excess heat. And same at higher temperature. Let me show you a blow up of that. Here it is. It's better. So the power input is 36 watts. Let me see, I'll be moving here because I can't see anything. Okay, I start from here, 282 degrees C. I add 7.7 watts, get here, and the excess power is here, the green line. So I have 3.5 watts, that is 45% excess. Same thing here, I've done 3 experiments, starting from this point, at higher temperature, 360 degrees, and I get this point. Now this is with the temperature. I can do the same thing with the voltage. And they give pretty similar results. I mean, it's not exactly the same. You have 25 instead of 50, 45. Here it's slightly higher. The average is about 33%. This has not been optimized at all. My calorimeter is not well suited to work above 400, 450 degrees. I have to modify it to improve that. But it worked pretty well. If I put hydrogen in it to check if anything happened, and I put hydrogen, there's no excess heat. So it's a good sign that, so it gives me 3 indications that something is happening in the system. I started this experiment first time in 1993 when I was at Berkeley, at Lawrence Berkeley Lab, doing the experiments without telling it to my professor, someone who was really against it. So I did it as I could. And then when I got some results, and when I came back, I worked with Longchamp in Grenoble, and we did the same. He didn't believe into my results, and so we repeated the experiment together. And we had a different design as this one. Calorimetry was different, and we had a viewport so we could see what was happening inside. And to our great surprise, at one point, passing the current through it, the lanthanum oxide became red, like hot. It looked like hot. Actually, it was luminescence. It was not temperature. It was really hot. So something was happening. I couldn't see it. In my new design, I couldn't see the color because it's all closed. But we see that. So at one point, I said, well, why not put a film to see if the X-rays are coming out? So I had, at that time, we had Polaroid still, so I put the Polaroid film with this black envelope. I don't have the picture here because I thought about it just last week when I was in China. But what we observed, the film had white traces on it, where it was in this black paper cover. So probably some X-rays are coming out of the system when it runs. So results. So this is not the first time, this is at least the third time. Mizuno has done something very similar back in 1993 also. We have observed excessive with deuterium, no excessive with hydrogen. It is reproducible. I've done it. I did do it 100 times to check it's 100 times, 100% reproducible, but every time I do it, it works. And then probably light and X-ray emission. The crystals I'm using now are single crystals made by a complicated technology that are difficult to reproduce. And the other thing, what happens is that there's such a temperature difference between the cathode and the anode side of the crystal that it breaks into pieces. So I cannot use it more than a couple of times. It breaks up. So I think I need to go to powders. I'm preparing experiments now to change and go to powders and also to go to higher temperatures because the higher the temperature, the higher the current. So the power input will be less because the voltage will drop when the current increases. So this is a system which is not static because I always need to put current and we can control the reaction. So I think we have here a good design to have something that can work at high temperature and possibly application in the future. So thank you very much.
Thank you. So we will have questions and comments. Okay. 9 minutes, please.
Yes.
Jean-Paul, the experiments with liquids in lithium that Gennadiy has reported shows effects in both cases, both in the crystalline form and in the liquid form, where he's doing DD scattering. Why in your system do you need a crystalline lattice? What's necessary with a proton conductor? Why can't you use a liquid? Is there a liquid version?
No. Wait. Probably the loading. If you have, I don't know, now we have to think. If things are happening in vacancies in the material, in this case we have vacancies where you can put at least 3 deuterium, because each lanthanum has a valency of 3. So you can put 3 deuterium instead of 1 lanthanum. That way it becomes white again. So when you are on the cathodic side, you will have more than 3 in each vacancies. So you are in the best situation where you have plenty of oxygen atoms in the cage giving out electrons, and you have the dynamics because it's flowing. So the deuterium is continually flowing in and out of the system and recycled. So I think this is a very important issue to have these dynamics. When I was working with Longchamp, we did experiments where we were sending pulses of 1 second every minute, and that was enough to get the same result. So we had a better higher COP. I didn't do all these things yet because this is very new. We did it just before coming. But that will be done in the future.
Okay, thanks.
Okay. So I think it's necessary to make a general remark about the proton conductor or everything. We used for a very long time electromigration, but this migration of electrons or deuterons means proton.
Yes.
So this is, but I think the people didn't realize that when there is electromigration, we migrated protons.
Oh.
So I think at this point is not so clear. But remember, the first experiment of Professor Ken, or the student Ken, was electromigration of hydrogen inside palladium wire. So this is what get the anomaly, when the protons or deuterons are moving, so are in not equilibrium condition. This is, I think, the key point of all the cold fusion. Sorry, use the old name, but is it? Okay.
I agree fully, but in this case, you don't even have the electrons moving, only the protons are moving. I mean, the deuterium are moving.
Yes.
This is
why because what? Because the deuterons or protons are moving.
Yeah, that's true.
Next, please.
Yeah, Jean-Paul, did you try any alternating your current? And that way you distribute the heat on both ends?
Yeah, I tried that and it didn't work. And I realized that you need to load it in one side, then you can push them on the wall, you know? And you have no choice than the fusing. If you change the direction of the voltage, then you have less density of material, I guess. So it didn't work as well. So I tried what you said.
Okay.
It worked.
Yeah. Maybe if you tried it longer,
Maybe,
I mean, very long DC,
Oh,
and
no,
then change it.
if you change cathode anode
Yeah.
after 1 hour, so yeah, you have to do that, sure. But the crystal, I think we break. I have to go to power anyway.
All right.
Okay, so
Thank you. Just one question, please, was to put in your cell the trap detector CR39 to see if there any radiation.
I don't know if the R39 will stand the temperature. Because
Yes, well,
yeah.
carbonate,
I
yes.
have to put it outside maybe, yeah, not
Outside.
inside. The neutrons will go
You
through
can
it.
see exactly where coming from the cell.
Yeah.
Later.
I'm not very familiar with the R39 myself. I've never done experiments with it, but why not?
Yeah, okay.
That's a good idea. Yes.
You made the comment about no excess heat from hydrogen,
Yeah.
but what kind of statistics? In other words, could you have 1/10 of the heat and it would just not be, because this is something that has been commented before. My expectation is that hydrogen will do it, but at a much lower level and probably below the statistics. Is that a valid statement?
That's about it, statement. As you can see, I'm not very precise in calorimetry. That can be improved in the future. There are many ways to improve the calorimeter and sensitivity by increasing the amount of material, going to higher temperatures. You need to be high enough so that conductivity happens. So I'm very optimistic in changing the temperature and maybe getting some effect with also hydrogen. It will be lower. I mean, if you look at the curve carefully, slightly above, but it's really slightly, so I won't bet anything on that.
Thank you.
Interesting work, thank you. I have a question about, you're saying you have breakdowns in your crystal.
Yeah.
How long runs are you, these successive events, how long time are we talking about?
Talk about 4, 5, 6 hours, something like that.
Okay.
on the average, yeah.
Thank you.
But when I was working with Longchamp, we were working at very low current, and we didn't have this problem. Now I'm working with higher currents. I'm applying like 50 milliamp, I'm sorry. I have a power supply that gives me 1,000 volts, 50 milliamp maximum. So that's the one I'm using. And you need, interestingly, you need to start with high voltage to trigger the experiment. If you start with low voltage, it doesn't even happen. So I start with high voltage, and all of a sudden current increases rapidly, and as my power supply is limited to 50, this levels off at 50. And but maybe you have to play with power supplies and the voltage and things like that to improve that. And also pulsing it. I mean, there are many parameters to be played with.
Thank you.
Okay, thank you.
okay, thank you very much. Thank you very much, Professor. So the next speaker is Dr. Melvin Myers. The title is Features of Fleischmann-Pons isoperiodic calorimetry.
Okay, I'm going to have to go fast because I have too many view graphs, but my email address is here if you want to send me an email. I'll be glad to send you the presentation or give me your card, and I'll send you the presentation when I get back. My short confusion review is Fleischmann ponds were dismissed by very inferior worth, calorimetry, especially at MIT, Caltech, and Harvard. And this is why we're in the position we're in today. Because Fleischmann ponds were correct, and they were more accurate and better in calorimetry than any other group at that time. And even today, nobody exceeds their accuracy in their calorimetry. And sometimes scientists get us wrong, but often important discoveries are rejected for many years. Well, we're now at 26 years, who knows how much longer it's going to take. Why is this topic important? It's a major cause of the 1989 controversy. It's poorly understood by most scientists, even cold fusion scientists often make erroneous statements about the Fleischmann ponds calorimetry. When properly applied, it's very accurate. Fleischmann got down to plus or minus 0.1 milliwatt. And it could be applied to many other electrochemical processes if it were accepted. Martin Fleischmann, outstanding in mathematics and modeling. And a lot of equations are in this presentation, but like I said, I'm just going to talk about them, not go through them. The Fleischmann ponds pure cell, I use this in NHE in Japan, and it is the one you see in some photos like today, is short and fat. That was more for display and pictures. But their cell is narrow and tall. The one I used in Japan, in diameter 2.5 centimeters, height 25 centimeters. And this makes good stirring possible. The narrow design, the gas is coming up. Here's some advantages of the Fleischmann ponds calorimetry. You can see right inside the cell. That's a big advantage. Heat's transferred by radiation. There's no memory effect. They just leave the cell. And it's safe, self-purifying, high accuracy, and it covers a wide dynamic range in voltage and power. In doing calorimetry, you measure four things: the temperature of the cell, temperature of the bath, the current of the cell, the voltage of the cell. The least accurate measurement is the temperature, and your calorimetry is often limited by that temperature error. They calibrated and they reported their values to 0.001 degrees. I only go to 0.01, Caltech 0.03, and MIT Harvard 0.1, and so, for example, MIT can do no better than plus or minus 10 milliwatts. Their actual error was actually 50 milliwatts that they reported. My error is, best I could do is plus or minus 1 milliwatt. I'll show you some data a little bit later. My error is usually around plus or minus 3 milliwatts. You have power going into the cell by electrochemistry, heater power, and any excess power. You have power going out by radiation conduction, gases that escape, the heated gases, and by work. And so you can write the equation in this form. If I wrote all these terms out like Morton often did early on, it would take almost a full page. But that's a shorthand version of it, and just give a few examples of some of these terms. I also got 30 pages of notes that Martin Fleischmann sent me on his. He analyzed how the temperature increases when you first start the experiment. In the correct answer, you have to assume that the radiative heat constant and the heat capacity, they change with time. And that's the correct assumption. You get simpler assumptions. Early on, it doesn't make any difference, the assumptions. Later on, if you make the simple assumptions, you get a constant temperature, but the actual behavior is that the cell temperature never reaches a steady state temperature. It keeps decreasing. Around here, you usually make up D2O, but you never reach a real steady steady state temperature. And it's linear in the early part, and the slope is given by this, so you can get some information out of that as well. If you start with the cell temperature and the bath temperature is the same when you turn on the current, you can study the heating, how the cell heats, linearly at first. Okay, there you go. I think maybe I went too many. I'll go back. Okay. The lower bound is what Martin and Weissman Pons often use this. This is an important paper. You can read all about it in this physical letters A paper. But they assume there's no excess heat. Here's the correct equation. You can assume the excess heat is 0, and then your constant has to change to compensate for that. It has to be less. If the power is less here, the constant has to be less here, the negative and the positive, both are less. So you get a simple equation which is very accurate. This is actually as good as you can do if you use the differential equation. You just calculate the constant based on assuming no excess power. A little error here, if this is radiation here, that has to be power due to radiation here. But you can do calorimetry without knowing your cell constant. You can calibrate as you go, and the highest value you get for the constant, assuming no excess power, will be close to the correct cell constant. So if you do this, you rearrange this equation, you see that early on, this is a very small, the FT, or temperature of the cell minus the temperature of the bath if you're doing heat conduction. And so it's very small, so you can get a negative value early on. And so it goes from negative and gradually up towards the correct value. This is an equation kind of like y equals a minus b over x. If you have some excess power, and early on you have excess power due to loading. So you get that with platinum in water, regular water, or heavy water. You don't see that if you use platinum, because there's no loading early on. And you can get ideas, you can get information about the loading, heat of loading from your experiment. This is my example of a study I did this summer using the lower bound. I'm hoping to get a negative value, but as soon as I took the first measurement, it's already 0. But it gradually goes up. There's some excess heat produced early on, so it kind of goes up jaggedly. But I get the regular trend is like this. This is getting close to the correct value. As time goes on, your difference in temperature gets larger, and you approach closer to the correct value. I calculated we do the loading to 0.6 in about 50 minutes, and we get a big jump right here around 50 minutes, where the excess heat to the loading becomes smaller. And so you get a lot of information. Just assume there's no excess power and calculate your constant. My constant is for heat transferred by conduction, because that was the type of cell I was using. This is the heat from that experiment. Early on, we see excess heat. I should not have been this high for the first day due to loading. Loading was about 6 milliwatts. So there's excess heat early on. Then I increased the current. I got a larger effect. And then I added D2O as usual. Sometimes it goes down because of cooling or contamination by hydrogen. And then it goes back up. This is the high point, about 73 milliwatts. Not really high, but I was using a very small electrode, and assuming 1 watt per cubic centimeter, that's 3 watts per cubic centimeter that I was getting, more than I expected actually. Then I added a lot of makeup water, cooled it down, dropped it here, came back. Then I did cooling. I turned the cell off and let it cool, and then added more water, heavy water, and started up again. But the next day I came in, it was actually minus 23 milliwatts. Down off here, and I know that's an error. You should never get a negative value, actually. So I realized I had not been calculating the heat due to gases or the heat due to work, because I wanted to simplify it. And now I put a high current and a higher temperature. And when I added that calculation in, The gas, due to the gases going out, is 18 milliwatts. The work was 5 milliwatts, so that brought me just close to 0, 0.8 milliwatts at that point. So that got rid of the negative value. This is when I cooled the cell down, you get a nice exponential decrease, follows this equation, involves the rate constant and the heat capacity. This is comparing the experimental cooling rate with the theoretical. If you have excess power, it'll cool slower. If you have endothermic deloading, it'll cool faster. And I might have had a little bit of that there. It was a little faster than expected. This is the experimental, this is the theoretical. They agree pretty well. Early on, you can always see that the temperature when you first start, the cooling curve, is changing linearly with time. And you can understand that by, if you have a small exponent, e to the minus x, a good approximation is equal to 1 minus x. And when you do that, you get a linear effect. So as long as that approximation holds, it's fairly linear. This is a little faster cooling than expected, and here it deviates from the assumption you made up here. Now you can integrate these equations, and this is a good test that this part of the equation is correct. You turn the current off, I0, everything else is 0 except the heat capacity term and the heat transfer term. If you integrate that, you get this equation right here. If you do it for radiation heat transfer, it's a little harder integral to solve, and you get this longer equation, but still you have the main term in the first log term here. These are just small correction terms. So the behavior is quite similar. In fact, this right here acts like a conductive term. If you had the heat conductive equal to this term right here, and the same heat capacity, you have the same straight line for the cooling curve. Just quickly, if you write the temperature as the temperature back plus the delta T, and put it into this equation and expand it in a binomial expansion, you get this expansion. In another form of this exactly the same equation, it's the exact equation, you notice the first term in the expansion, the delta T, the first power, acts as a conductive term. The temperature back to the third power times the radiated heat transfer coefficient is the conductive unit. And that's the same factor 4 we saw when we did integration. So it's kind of interesting that it appears both places. Now, if you plot this out according to the integrated equation, you get a nice straight line. Look at the R value, 0.9999 and more for the cooling curve. And if you had heat after death, you get a departure from this. But I apparently did not have enough heat after death for this to show up. This is for the second thermistor in the same cell, another straight line, very similar, a very similar high R squared value. It shows that that equation covering the cell cooling. Heating or cooling the cell is covered very accurately by the Fleischmann-Pons equations. In some places, I think I read where they state that calorimetry doesn't work until you reach a steady state temperature. That's not true. It can easily cover going through a heating pulse or going through any temperature change. I need to go back to this quickly. This is a cell after the experiment, and the electrode came out very bright, and Pons has told me when he does not use lithium in the electrolyte, you don't get a dark color on the cathode. He thinks the dark color is due to lithium depositing and reacting with nitrogen introduced when you add heavy water. Nitrogen gets in the cell, you form lithium nitrides. Lithium nitrides are dark color. No lithium, no dark color on the cathode. This is the actual cell after the experiment. And if you have heat after death, like in my plated-boron experiment done in Japan, NHE, this is theoretical cooling. This is what the cooling we see. And we even saw self-heating, or heated again. So the cooling curve is a good way to identify heat after death effects. in a lot of Martin Fleischman's paper, you see this, where he does a numerical integration, and he plots the data out, and you extrapolate to zero, you get an intercept that gives you the self-constant. Some people said that's too many different figures, but he actually can extrapolate and get that accurate value by his method. And it took me a while to figure out how he got this equation. This is the way he does it, algebraic rearrangement. Substitution here is important. It makes the slope about 1. You guess the heat capacity, and if you guess correctly, the slope will be 1. And this is the final equation, is where you have integrals. It's an integrated equation, and his data, integrated data, going through a heating pulse, and temperature changes, gives you a nice straight line, and this is the straight line equation. You can easily combine heat production and heat radiation by just increasing the constant slightly. This is the power term for the change of temperature to calorimetry. Early on, the mass of the detail changes as well, and so you have to take the derivative of both the temperature and the mass, and it gives you a more complicated equation here. In the early pages, you'll see this. Later on, Mark went to this simplified equation. This is a small term, and so that's a good assumption, but this is the exact equation.
Would you conclude?
Okay. This is a power term for escaping gases. And that's a complicated term, that's why I left it for last. You can do it with a hand calculator, but it's tedious. It also involves the pressure, atmospheric pressure in this term. As you see here, the pressure inside the cell is made up by these gases. In this term, you need to know the atmospheric pressure in order to, this P prime here is your vapor pressure, water, and this is the atmospheric pressure. And so you need to measure the atmospheric pressure if you're going to do this equation correctly. And I know very few groups have done this. This is how all the things you've got to watch in getting high accuracy. And this is the summary. And I will take time to read through it. You can read through it during the questions. Thank you.
Thank you very much, Dr. Miles. So, any questions and comments?